Dear participants, good morning to one and all present here. I'm very happy to welcome you all for the second day of Atal sponsored faculty development program on augmented reality and virtual reality, organized by the Department of Computer Science and Engineering, Dr. Mahalingam College of Engineering and Technology, Coimbatore District. I am very happy to introduce our today's session head, Sri Neelargaya Mandal. He is an application developer at ThoughtWorks, Kolkata. He completed his Bachelor of Technology in Computer Science. Now he is a full stack developer. His other experiences in fields include Unity, C#, Java Spring Boot, Vue.js, Unity 3D, Python, etc. I'm very happy to welcome you, sir. I kindly request you to please take over the session.
Thank you.
Thank you, sir. Thank you. Thank you.
Okay, let me share the screen. I'm guessing my screen is visible.
Yes, sir, it is visible.
Okay, thank you.
Thank you, sir. Thank you.
So good morning, everyone. It's really good to see that so many people actually showed up, and that too on a weekday morning. And shout out to the organizers for doing this great job at setting up this platform. To give a brief introduction about myself, I'm Nilarg Mondal. I'm a consultant at ThoughtWorks, Gurgaon. And I've been in this AR/VR space for almost 2 years now. And the topic at hand is computer graphics. Now, this is a bit different from the computer graphics we go through in our colleges and school, which is mostly related to transformation of matrices. But what we'll look into today is mostly around 3D computer graphics. Although, to be honest, the matrix transforms are what run under the hood. So to split the topic up, there are three major sections of 3D computer graphics: but the modeling, the layout and animations, and the rendering. So we'll go step by step. We'll start off with modeling. And what modeling is that we have different objects in our real environment, right? In the real world. Now, in order to represent them or display them inside of a computer, we need to convert them in a certain format of data, right? Because computers only understands the bit 0 and 1. So the process of defining a real world object into its mathematical representation in the 3D space is what is called modeling, not to be mixed with the other profession of modeling. So in order to do this, we use multiple different like specialized softwares or 3D modeling softwares like Blender, Autodesk, Maya, to name a few. There are way more. Now, in order to represent them, there are certain different forms of representation. The two major sections of representation are the solid representation of models as well as a shell-based representation. What a solid representation of a 3D model means is that the 3D model is divided into what is called voxels. Now, when we talk about 2D images, we always talk about pixels, right? That is the smallest unit of a 2D image. Similarly, a voxel is the smallest unit of a 3D element. It's essentially a cube rather than a square for a pixel. So when a model is represented by a set of voxels or the set of the volume of that object, it is taken to be a solid representation of that object. Similarly, models can be represented not by their volume, but also by their surface. In that representation, it's called a shell-based representation. So whenever developing a new application or let's say game or CGI for a new movie, shell representation is always preferred more than solid representation, mainly because when rendering of solid representation is done, there are lots of parts of the solid representation which don't actually get shown. For example, if we are looking at a cube, only half of the cube is visible to any viewer at any point of time. The extra volume that is behind it is essentially unused, unnecessary. So a shell-based representation is mostly used. But during development or during sculpting of these models, volumetric or solid-based representation is used quite often. We'll go through the different processes of building these models as well. So to go into a bit deeper with representation, there are three major types of representations. Polygonal representation, which means that the model itself is divided into smaller polygons, which constitute of line segments, which are defined by two vertices to form a 3D mesh. Similarly, we have the curve modeling, in which each surface is defined not by the polygons that construct that surface, but by a singular point at the center of the surface and with some weighted control points which influence the curvature of that surface. Similarly, there is the process of digital sculpting, which is not exactly a representation, but more of a process of building models, where people essentially are able to grab, stretch, pull, or do whatever with the simpler shapes to build more complex shapes out of it. Now, digital sculpting has two types of representations, which are displacement and volumetric. Volumetric representation can be thought of as how the shell representation is done. Now, all these operations that we do, the pull, push, smoothing, or grabbing of the model itself, operate on top of the shell. Then it's called a displacement based digital sculpting. While if all of these operations are done on top of the volume and change the volume of the object, it's called a volumetric digital representation or digital sculpting. So there are multiple techniques in which modeling is done. There's a very simple technique of constructive geometry, where complex geometry is subdivided or reconstructed by the use of smaller, more simpler geometry. Like this complicated shape here is can be broken down into the combination of a cube, a sphere, and three cylinders. And these simpler geometries are combined using Boolean operations. Like you can see that there is an intersection of the cubes while there is a differentiation between these two shapes and union of other few. Why use such a yeah, why use such a form of or technique of building models? Well, is simply because when you are trying to represent a simpler model, rather than representing the mesh that combines to form that model, they can be represented via a equation. This is called implicit surfaces. So on the left, I have a torus, which can be defined by its mathematical equation. And rather than saving the entire set of different points on top of this surface, one can also save the the different parameters and variables inside of the equation to reconstruct these surfaces. These are what are called implicit surfaces. So simpler shapes like cylinders, cubes, spheres are mostly represented by their implicit surfaces or equations rather than meshes or volumes. Similarly, there is a process of subdivision of surfaces, which essentially defines that if you have a good enough amount of meshes, you can subdivide them to form smaller meshes, which give you much smoother surfaces. Now, when it comes to rendering, rendering is dependent on the number of polygons that you show in any single frame. And in order to reduce the number of polygons, a lot of the time, optimization algorithms like subdivision of surfaces is used, where you use less number of polygons, but you still provide a much smoother surface to view. So modeling by itself is kind of just building the bare bones of any digital object. Now, in order to impart any life to these objects, every object needs to have a certain amount of texture on top of it. Now, textures are simply details details about the surface texture or the color that is imparted on top of the object. As you can see on the left, this is a model taken from Last of Us, I presume. Uh, so on the left, you can see that the model is very bare basic, while on the right, along with textures, it looks a lot more lifelike. Now, every texture can be assumed to be a 2D image, no matter the type of texture. We'll get into the types later on. So in order to map these 2D images or wrap them around the 3D models that we create, what we use is called a UV map. The UV map is a set of like data points which essentially say which part of the image gets mapped to which part of the 3D mesh. Now there are many different types of meshes that constitute our normal like all the CGI and all the 3D graphics that we go through. The most simplest is the diffuse map, which is essentially just color mapping. For example, you have a sphere, you have the map of the world. If you combine them two, you get a globe, right? And you can consider the 2D map or the world map as being the diffuse map, which is just the color attribution of the 3D model. Similarly, you have height maps, which can be differentiated into bumps and displacement. What height maps gives you are different positional differences of the actual vertices uh, of a mesh. So on the right, as you can see, this is actually a singular mesh. This is actually a simple plane mesh, but it is the bump map or the displacement maps which give it the illusion of depth and height on top of it. The difference between bump and displacement are that bump maps essentially play around with the light that is falling on top of it to give you the illusion of a depth, while displacement map actually move around or displace the vertices on top of that mesh. When it comes to specular and reflection, I'll talk about both of them together. So specular maps are the maps that essentially determine how light gets reflected or the amount of light that gets reflected off a surface. So it might be like sound a bit counterintuitive because the next is reflection map itself, but I'll try explaining it well enough. So the amount of light that gets reflected off a surface is determined by a specular map, while what you see as a reflection on top of a reflective surface is defined by its reflection map. So for example, if you have a glassy surface, it might be metallic like this, which is not exactly showing us any features behind it, but it's reflecting a certain amount of light. That is a specular map in action. While any surface that is glassy enough to show the details around it, even details that are not inside of the camera frame, is what's determined by the reflection maps. Apart from these very maps, there are way more different maps like baked light maps or even occlusion mapping. Now I can show you actually what's occlusion mapping. So as you can see, the hair on this character is actually different planes. These are like paper kind of models, but the texture that you see here is like hair strands. This is done by occlusion mapping. What occlusion mapping does, it essentially punches holes inside of your model to give the illusion of like more sophisticated models, in spite of the fact that the models itself might be much more simpler underneath. Similarly, you have light mapping, which essentially bakes the light information of your environment on top of the model itself so that it's much more optimized, because light calculation is always very expensive. When it comes to rendering, we'll see why. So that is kind of modeling and texturing and how it's done. The so once those models are actually created, they need to be aligned, right? They need to form a different scene in order for us to, let's say, tell a story or give the feeling of us being inside of a virtual space. They need to be aligned with something, a frame of reference, and this information is stored in what is called a scene layout. Essentially, scene layouts are the spatial data in which spatial information about these different models and how they are constructed and positioned around in the environment, in the virtual environment. Now, the spatial layouts of individual objects can be broken down into three simple features: the location of the object, that is the position where it is, the rotation of that object, and the scale of the object. These three together form what is called the transform of an object. Now, the transform component, you might get a bit more feel about it when you go through the Unity tutorials and all that. And it essentially determines where the object is placed and how it is placed. These information are taken into consideration during the rendering process as well. Now, in order to go through, apart from like the models itself and the positions they are, most of the time when we are working on applications, in order to make them interactive and feel more lifelike, we'd add animations to them, right? And animations are considered to be the temporal data or the data that you impart on it over a time frame. Now, there are many different ways in which animation is done. When it comes to 3D animations, uh, normally a rig or a skeleton of the 3D model is created. Now, skeletons are created via bones, which are essentially line segments that represent a part of the model itself. For example, if you had a bone for the knee or the leg itself, all the meshes, all the model around this uh, bone will be deformed depending upon the position and rotation of this bone. And multiple of these bone structures together form a skeleton of a model. Now, as a standardized practice, every model is kind of built around a certain pose. It's called the T pose. This is meant so that content creators or model artists can create different models which are independent of the skeleton that is created with them. Why is this used? It's used mainly because the models themselves are so the models themselves can be replaced with other models over time. So essentially using the same rig or the same skeleton over multiple models to impart the same animation on different models. That's the concept of rigging and modeling. Now, apart from rigging and modeling, there is the methodologies in which the animations themselves are created. The most simplest is the keyframing, where we go from frame by frame and settle on how the animations actually look, the procedure of setting up the animation. Other than that, we also use motion capture, which is mainly used for more complicated behaviors like, let's say, facial expressions or dance moves or any actions which need to look very fluid and human like. We go for things like motion capture. Now, apart from motion capture and keyframing, there's also inverse kinematics and procedural generation. This is where animation kind of marries programming, and not like the entire animation is not hand built, but instead they are created using smaller programs which essentially generate the movements themselves. As you can see here on the lower right corner, there is this mechanical arm which is animating, but it's animating in dependence with this object that is trying to track. And what's happening here is that the motors and gears inside of this mechanical arm are moving so that the head of the arm can reach the point or the end point of this target object. So this is called inverse kinematics, and similarly, loads of inverse kinematics can be combined together to form what is called procedural generated animations. These are animations that are not hand coded even a bit, but completely built from generating programs. Now, loads of times they are based on very simple algorithms, but sometimes they even use things like machine learning to kind of impart a sense of naturalism or realism to the models itself. Where are these things used? Most of the times, these are used for different characters during runtime rendering. For example, if a character has a walk animation, which works only on flat surfaces, whenever the character hits something like a bump, its leg will go through that small bump, right? In order to get over these problems, which break the immersion of the animation, a lot of inverse kinematics is used, where you essentially triangulate where the foot should be, and according to where the foot should be with respect to the bump on the ground, you adjust the knee and the hip joints to give the right type of animation to it. And yeah, so whenever animation is actually done, they're never really done like as individual pieces, but it's mostly a combination of all of these methods, not just a single one. So you might have parts which are keyframed, while parts which take up motion capture, like the body might take up motion capture, while the face might take up keyframing. And you can have inverse kinematics to rotate the body towards a certain direction where the animated object might be looking. Similarly, so that's mostly about animation. Now comes in the major part, which is rendering. Now, once all the models are created and generated, they need to be rendered. So, what rendering is that is the process of converting all of these 3D virtual objects that are inside of the space into what we see. So everything that we are seeing right now is a rendered image, right? They are 2D pixels on a screen. Now, in order to convert all of that data that we just created using the models and the animations, all of that to be converted into a 2D image, the process is called rendering. So, how rendering works is a bit different from how we see objects in real life. So when it comes to real objects, we normally see real objects by the light that is reflected from those objects. Now, till this point, everything that we had in our virtual space was essentially representations or numbers inside, and not actual physical objects which can reflect light and like be visualized on a screen. So, in order to get a visual representation, what we normally do is we send out rays from the viewport, and they traverse through so from the viewing point, and they traverse through the viewport onto the scene. Now, these rays that are cast, they then get refracted or reflected off of different surfaces to give us a sense of how the scene is inside of the virtual world. Now, there are different processes of doing it, and the major techniques are image-based ordering and object-based ordering. As referred before, each of those models are converted into different polygons, and each of those polygons have a certain amount of space they are taking on top of the frame or the uh, like rendered image. Now, in order to go through like mapping all the pixels on the screen, we can do it in two orders. The first order is by going through iterating through individual pixels on the image plane, which is called image ordered algorithms. And the other way of doing it is via object ordered algorithms, which is after we calculate as to which objects are there inside of the screen itself, we only iterate through the surfaces of the objects at hand. Now, intuitively, it might seem like image ordered rendering might be faster because we have only a distinct amount of pixels. But given that every pixel is not just one object, but a combination of multiple, it's always more efficient to go from a object ordered algorithm. Now, each of these objects inside of the scene have their own surfaces, right? And each of those surfaces somehow relate to different, uh, like react to different light conditions and different textures that are formed on top of the screen. And loads of the time, there are empty spaces inside of the pixels where there are no objects blocking that gaze. So in such cases, ordered algorithms are much faster than that of the pixel ordered or image ordered algorithms. Now, there are quite a few processes in which rendering is done. For example, rasterization is the umbrella term in which it converts the geometric projections of these objects into different pixels or rendered maps. And we have ray casting, which we discussed a bit before, where a ray is essentially launched from the camera itself towards the scene, and wherever they hit, and whatever reflection, simple laws of reflection and refraction are taken, are processed to form an image on top of the viewport. Now, ray tracing is similar in the sense that it also uses rays, but instead of casting a ray from the camera or the viewpoint itself, what it does is starts building a simulation. With every ray that is cast, it kind of simulates that these are the lighting conditions. So it starts approximating as to how the image might look over time. There's also the concept of radiosity. What radiosity is how the rather than calculating the rays that come out of the image or the camera viewport, it uses the light sources or illumination of the environment itself to create the different light calculations. So that's the different types of rendering techniques. Now, finally, we come to the rendering process itself. Now, in order to understand the rendering process, we need to understand that this process is done continuously for real-time rendering. Real-time rendering are things like games or applications, 3D applications, which needs to show and give us the feel of being in a 3D space in real time. While there is also the process of baking or pre-rendering, which is done mainly before production, before the actual final product is created. These are things that are done like in CGI movies or animated movies. And the rendering pipeline itself can be broken down into four major sections that are vertex transforms, geometric stages, raster stages, and pixel transformations. So vertex transforms are where the model is essentially translated from the model space to the world space. This is done using the layout information that we saw in the layout scenes. And this relative information with respect to the world space is converted into the camera space. Finally, we get the clipping space. So camera space means that how the objects are essentially built or how they are constructed inside of the scene with respect to the camera itself. Clipping space means that the viewport inside of which the field of view that the camera looks to is the viewport. And clipping space just means everything that is inside of that viewport. So it starts rejecting all the surfaces, all the different objects that are outside of this clipping space. So once these vertex transformations are done, they go into the geometric stage where each 3D object is projected as its geometric copy on top of the uh, image itself. Now, the vertex shaders and the geometric shaders, or if you go for game engines, they are also called fragment shaders, are programs which essentially convert these points into geometric constructs of themselves. So there is quite a bit of calculation that is done to convert the different individual points to geometric constructions and impart certain amount of lighting conditions to them. Finally, we go into the clipping stage where all of these geometric shaders, after they have deformed the actual model, are clipped off based on whether they are part of the uh, frame or not, image frame or not. Finally, we have screen mapping, which essentially converts all of these projections on top of the screen essentially saying that this object will take up this space inside of the screen itself or the rendered image itself. Finally, we have triangle setup, which breaks down the meshes into smaller triangles, which is why in many models you will get that there is a certain count of triangles associated with the model. This is where the triangles are set up. Finally, we go through the triangle traversal. This is part of the rasterization step, where each of these triangles with their individual vertex colors are converted into pixels or rasters. And pixel shaders essentially run on top of the pixels that are created from the triangle traversal. Now, after all of those pixels are shaded and colored, they go into the merger, which compiles all of these pixels together to form the image. Finally, it goes into the screen space, which is the space that we see. And all of these images that just got created out of the merging experience are then blended with other layers. Now, this is where all the layering and the different render calls are done or mixed together. So this entire process of the rendering pipeline is done mainly in the GPU, and it's done almost every frame, actually multiple times every frame with every render pass. What a render pass is that for every different type of material or different types of lighting, it needs to do these calculations at least once. And there are processes like batching, which are used for optimizing them or coupling multiple of these render pipeline loops into them. And this final stage of buffering and blending is where they are mixed together. The Z buffer here represents the distance, how far an object is from the camera itself. This is just so that the objects that are further away are blocked by objects that are closer by. Essentially, gives us the understanding of occlusion. And once all of the pixel transform and shading is done, we get our final images. Now, each of these processes take a certain amount of time, and reducing the time is what we always tried for when building augmented and virtual reality applications, mainly because the devices we are working on are not PCs which can take high fidelity graphics, but much more simpler things like headset and mobiles. And the optimization part is always done during these shaders and mixing of the shade. Also, batching is used quite a bit. But mainly, why do we need to go through all of these processes? Because every augmented and virtual reality application is based off of a certain amount of immersion that it imparts. Whether it's the kind of immersion that comes out of like interacting with objects or just visually seeing those objects. When we are in a augmented or a virtual reality space, it's always has has to look realistic, or at least impart the feeling that it's not something that is uncanny, that is outside of the real world, something that can exist. And in order to do that is why we go through all of the 3D graphics part, because we are always trying to create experiences rather than applications. So I think I'm really early on time, but yeah, that's all I had. So thank you, everyone. Largo model, feel free to ask any questions if you have any.
I request the participants to kindly ask the questions if you have. So thank you for your wonderful session, sir.
Thank you.
Okay. Participants, you can also use chat box for posting your questions. Participants, if you have any questions, kindly unmute yourself.
I'm sorry, you're not that audible.
Sir, I couldn't get you, sir. Sir, you are not audible, sir. I hope Madan sir is speaking now. Your voice is very low, sir. Professor Madan sir, you may kindly unmute. Your voice is very low, sir.
So you can also type the question if you want.
Madan sir, you may kindly type your question in the chat box. Any more questions from other participants? Sir, there is a question in the chat box from Professor Satish Kumar P. We are new for this AR and VR. Is the simple software or tools available to experience the animation?
Yes, so if you're looking for simpler tools to get into AR and VR, I would suggest going for something like Unity, mainly because it gives you everything that is required from the rendering pipelines to the physics engine to all the lighting and shading. And in order to build graphics on top of that, you can go for either things like Blender, which comes free, so you can try things out there. Or if you want to work directly inside of Unity, you can use things like Pro Builder or I think it's Polybrush or uh, Pro Builder as well as Polygon Brush or something like that. The tool is called.
So,
And
sir, so this is R. Sudharma from IIT Technology. So
yep,
kindly type this software name in the chat box so that
okay, okay,
your
sure.
pronunciation and then spelling are the different. So
So you can go for Unity 3D for general. You can go for Unity 3D for general purpose AR development. Also, you can go for Blender for 3D modeling.
so are you typing in chat box, sir?
Yeah, is it there in the chat box?
Yeah,
I
sir.
just typed it. Yeah. You can go for Blender or something like Maya Max, although those are paid, I think. Yep. Okay, so normally you would have something like a .fbx file. So that's something that Unity picks up pretty well. But when it comes to actual mapping of the textures, Unity have something called materials, and different materials might react differently. So you can go for the standard material, which has the different maps like your albedo map, which corresponds to the diffuse map. You have the specularity metallic map as well as emission maps. Now, there is a certain option inside of Maya Max, I think, which uh,
Yeah,
essentially
sir.
converts, sets it for Unity, like build for Unity kind of options inside of Maya and Max.
FBX, sir. FBX.
Yeah, .fbx or .obj also works. Dot
No,
object formats.
dot FBX is in the file format.
Yeah, .fbx is the file format.
Okay, so if you want to play this one, we have to convert it into MP4 or what, sir?
Okay, so if you want to play it as a model animation, you like there is a render to a movie kind of option inside of Maya, I think Maya or Max. So it will convert your entire animation from a certain perspective into a movie or a MP4.
Okay, okay.
It is possible to import the 3D model created in different CAD model softwares, and how easy can utilize this legacy data to create AR/VR development. Okay, so when it comes to CAD models, normally they are pretty simple to import into your game engines or AR/VR building software. The issues that they normally have are with the texture mapping and the UV mapping. If the texture is registered or recognized by the game engine that you're working with, it's very easy. It's mostly like a drag and drop or import. But if the textures don't get mapped properly, you might have to work inside of the game engine to remap those textures. Okay. Yeah. Any other
Thank you, sir.
questions?
Sir Madan, sir, now you may unmute and try to ask your question.
Ma'am, I already asked my question, even though I'm asking another one. For example, if I'm creating a small bit of animation for a particular object, so I'm going to import that in a FBX file towards inside Unity. So, is there anything that I want to just simply save the file and I can convert it, like I can take it to FBX, or you know, really I have to do anything?
Sorry, your voice is breaking. So if I'm getting the question right, you want to convert that FBX into, like, essentially export that FBX into somewhere?
Exactly. While exporting my animation,
Hmm.
so like I can't see any animation in the Unity engine, but I did some animation and I'm taking the character towards inside Unity, but I couldn't see anything. Any animation is
Okay,
happening, just
okay.
the characters staying in the same pose.
Yeah,
So
yeah,
what
yeah.
is the thing?
So Unity's animation system is a bit like disconnected from this animation system. Inside of Unity, you will have things like you have an animator component, which essentially ties back to the animations that are inside of the file, and you have animation triggers, which which are essentially keys or
So
string
what
keys.
what is this software name, sir? Unity.
Yeah, Unity 3D.
Unity
Unity 3D.
3.
Yeah, Unity 3D. You
Whether
can also
whether it is available in all OS or Windows like that from
no, it's
Unity
available for
3.
all OSs. Yeah.
Unity 3D.
So it's
Okay.
available for Mac, Linux, I think Linux as well, Windows as well.
Okay, sir. Okay, sir.
Yeah. To complete the answer on that question, there is a like animator controller component inside of Unity, which ties back to the animations that you are building in something like Blender, and you will have to call animation triggers from code to cause those animations to play.
So we have to install both Unity 3D and Blender.
You can also build smaller or simpler low poly models in Unity itself using something like Pro Builder. So Pro Builder is a plugin.
So it's all Blender, Maya Max are open source, sir. So
Uh,
what is Unity 3D? Whether it is free or
so Unity
Unity?
3D is not really open source. It has a business model where you need to pay only if you are building something commercial or making a profit out of it. So you can use it freely.
Freely. So okay. Business model only we have to pay. For simple applications, we can use it freely.
Yeah.
Thank you, sir.
Hello.
Yes.
Hello, am I audible?
Yeah, you're audible.
Yes, this is Saran Kumar. So, is it possible to use legacy data which is built in existing CAD modeling softwares to experience this AR VR development? I
Yeah.
have a
So
number of
yeah, go ahead.
yeah. So the existing models which I already built in any of the CAD modeling software, which I want to import it in the Unity 3D, is that possible? How extent we can do that kind of development?
Yeah. So you're talking about Revit kind of models, right?
Not
Architecture models.
exactly. Is it AutoCAD, Creo,
Okay, AutoCAD models.
NX, like that, that kind of models, that
Yeah,
kind
they
of
can
softwares.
be freely imported into Unity.
So we have to convert into export it as a .fbx
Yeah.
OBJ format, or okay, if
Yes, you'll have to.
provided okay, that software has to have that conversion
Mechanism.
utility.
Yes.
Then if it is available, then we can export it.
Yeah.
Okay, export and we import can be possible.
Yeah.
We
Import.
can leverage. Okay, okay, thanks.
Any more questions from the participants?
Hello, sir. This is Hari.
Yeah.
Yes, sir. We have prefab images that is already prefabricated objects available in our Unity. For creating that object, which kind of software is more suitable, sir? Actually, to animate, we have this more animations and all. To do that, which software is more suitable, sir?
So prefabs in Unity are just like saved
Yeah,
objects.
yeah,
Yeah.
it's a saved object actually, created building
Yeah.
objects.
But inside of the prefab itself, if you want a more animated model, you would go for something like a modeling software like Blender, Maya Max, or ZBrush, things like that. So creating those models outside, then importing it in as an FBX files, then wrapping it inside of game objects and turning them into prefabs is the like best way to do it.
Okay, okay, sir. Okay. But we are facing some problem. Actually, what the problem we are facing while teaching to students means we need a configuration we need if you are using Unity means we need high configuration systems. For example, 8 GB RAM or 16
Yes.
GB RAM or
Yes.
some other thing. See, is any other software or open source that is available and which is suitable or which is working in minimum configuration?
Which works on a minimum configuration.
Yeah.
Uh, there's AR Spark, I think, which is from Facebook, which works at a lower configuration than that. It works similarly. It has quite a few configurations to build like simpler apps, which work on things like face detection or plane detection and things like that. So you can look into AR Spark.
Okay, sir. Okay, okay. Okay, okay, okay. Thank you, sir.
Yeah.
So Blender also works in 4 GB RAM, sir. Blender. I don't know about Maya.
Yeah. Yeah, Blender is lighter than Maya or Max. It might work on
Okay,
4 GB. It shouldn't be much of an issue, but you'd have to try and test it.
okay, sir. Thank you, thank you.
Thank you.
So hi, this is Madan again.
Yep.
So regarding Unity 3D, for VR AR, that will be fine. Okay, we are taking as an output and we are bringing all the models and lighting in the models, and the camera can move anywhere. But my question is, I cannot use the similar Unity as my render engine, right? So I can take it as a movie kind of a quality render. Like how to do that? Is there any information from you?
No, you can't render it like that from Unity. Like there are render textures, but they are not built for rendering movies out of it. Although movies are like smaller movies are made using Unity. So
Yeah,
there are,
like I heard, like we can do some kind of cinematic render through with the help of Unity. that I heard, but I'm not sure how to do that. So it's not possible, right? Is it possible?
I think it's possible with a plugin called Cinemation.
Cinemation.
Yeah, Cinemation. I'll
You
put
have to
that
pay
here.
for that, or like, is it available for the normal user?
Yeah, it's available for the normal users. So inside of Unity's package manager, you'll get the package for Cinemation. I think that's what's used for building this.
Gotcha. Okay. So, okay. Thank you, man. Thank you very much.
Yeah. Okay. Any other questions?
So good morning, sir. This is Gauri Shankari.
Yep.
So currently we are having Blender in our syllabus, sir, for students. Can you suggest any other latest to open source tools for our students? For animation open source tools.
Animation open source tools. You can look into ZBrush or SketchUp. They
Okay,
might be
sir.
lighter. ZBrush
Oh,
and SketchUp.
okay, sir. Thank you, sir.
Yeah.
Madam? Hello? Madam? From
Yes,
Yeah.
sir.
Kharagpur? Madam, could you please share your syllabus in the WhatsApp group, madam? Blender
You need
syllabus.
our syllabus, sir.
Yes, madam. Yes, madam.
Yes, sir. Yes, sir. We'll be sharing you shortly.
Okay.
Thank you.
Okay, madam. Thank you, madam. Thank you, madam.
Okay, sir. Okay. Any more questions? So if there is no more questions, we shall come to the formal closure of this session. I thank today's chief guest, Shri Niralgaya Mandal, for
Thank you.
delivering such a wonderful session, sir. Really, it was informative for the participants.
Thank you.
Thank you, sir. Thank you very much.